All right, so in this lesson, we are going to talk about comparing linear, quadratic, and exponential functions. We've learned about all three of these, and we need to talk about how they are different when it comes to their equations, to their graphs, to their tables, and to their real-world applications. So when we see word problems, how do we know what kind that we're looking at? So let's start with linear. When we look at equations, linear looks like y equals mx plus b. Remember, we also have standard form and point slope form for linear. So we can write ax plus by equals c, or we can also have, like I said, point slope form. So that's y minus y1 equals m times x minus x1. We should be able to operate in all three of those types of equations. Then we have over here, let's see, now we have quadratic, and we just learned about two different forms for quadratic. There is actually a third, but quadratic equations, this is standard form. We should also probably write vertex form in here, y equals ax minus h squared plus k. And the big thing for recognizing a quadratic equation is that the equation itself is going to have x squared in it. So that's going to make it look different than linear equations. And then lastly, we can talk about exponential functions. So exponential functions, their equations look like y equals a times b to the x. Now, a lot of times this would have a parenthesis around the b. I think it might be better to write it that way. And what identifies this one specifically as exponential is that we see the x in the exponent spot. All right, so now let's go back and remind ourselves what the graphs of these things look like. And this is going to be an example that's already written down that we can copy into our notes. So y equals negative 2x plus 5. Remember, this means we would start at 5 on the y-axis, and we would count a slope of negative 2 over 1. So that equation is going, or graph, sorry, is going to look like this when it is graphed. Right, you're starting at 5, going down 2 over 1, down 2 over 1. I noticed they didn't put all these points here, but this is what our graph should look like. And we can also go up 2 and left 1. Okay, and if we talk about the graph of this quadratic, which is what we've just recently been learning, all right, we get this equation right here, which we notice is in standard form. So to be able to graph that, we would have to do negative b over 2a. All right, so let's say that we've done all of that, and we have figured out that our vertex is at negative 2, negative 4. So we would go ahead and plot that, right? Negative 2, negative 4. Oh, I don't think I counted that correctly. Sorry, fix that negative 8. And then we're going to go up 1 over 1, and then the next move is going to be up 3 over 1 and up 5. That's what's going to create our curved pattern. All right, so make sure you have this quadratic down. All right, now let's look at our exponential graph. So on our exponential graph, remember that these always have to have a place to start. So this can be written as y equals 1 times 2 to the x. That means I'm going to start at 1. So this is my starting point, or my y-intercept. And then I'm going to multiply by 2 every time. So notice that is what's happened on the graph. They started at 1 here, and then they multiplied. This is at 2, and then at 4, and then at 8. And then we go backwards, we're at 1/2 and 1/4. Remember, these also have an asymptote line at 0, so they get close, but they never actually cross that 0 line. All right, so if we go back then, and I'll just work backwards from here, talking about domain and range. So domain for all of these, remember domain are x values. So my domain is going to be all real numbers, but my range in this case is y is greater than 0. That's because you can see on the graph right here that we start at 0. We don't even hit 0 actually, but all the y values are going to be greater than that. If we look at how that compares to the quadratic, its domain is still all real numbers. I'm going left and right forever, but its range is y is greater than or equal to negative 8. So notice this one is equal to negative 8, where on the other side it's just strictly greater than, because it never actually equals 0. And then we have the linear. This one's going to be the easiest. It goes up, down, and left, right forever. So its domain and range are both all real numbers. All right, so the next part is actually talking about patterns and tables. This part's kind of the most fun for me. So if we look at the pattern that's going to happen in this table. So take a second to pause the video, see if you can figure out the pattern. You should notice that this is subtracting 4 every time. Now, one thing that they haven't done here that I think we should do is we need to also check for consistency in the x column. So notice the x's are adding 2 every time. So if I do the rate of change here, the rate of change is going to be consistent, and the rate of change is going to be -4 over 2, or -2. So what we want to make sure we write down is that we have a constant rate of change. We're continuously adding or subtracting the same value, so you should write or subtracting, and we can call this a common first difference. So we'll see how that's going to change in some of our others. All right, so for quadratic, here's our example for quadratic. And so the same thing, I want you to find the differences. So notice in x, this is changing by y, or sorry, not by y, by 1. So this is a constant difference in x. And you should notice that if we find the common differences, this is +1, +3, +5, +7, you would expect that. If you went backwards 1, this would be +1 again, so it would actually go back to -7, right? Because this would be my vertex where I'm turning around. Okay, but if we look for the common difference between these sets of numbers, notice that these are adding by 2 every time, and we've seen this pattern before, but when we have a second common difference, that is something that lets us know that what we're looking at is quadratic. So we have a common second difference. So we have to do the difference twice. All right, and then lastly, if we look at exponential, we will see a pattern of usually of multiplication or division. So in this instance, we have multiplication. And this says there is a common ratio, so that term should also be familiar with you. We've learned this term before. But I would like for you to also write that this could as well be a pattern of division. And when we have division, remember that we end up having to use a fraction. So for instance, if the pattern was divide by 3, that's the same thing as having 1/3 as the ratio. Okay, so the last thing I want you to do is I need you to flip your paper over. We're going to write this on the back. So you should have, you're going to just kind of draw yourself or remind yourself of the different shapes that we could have for these. What we want to talk about is why we would use certain functions, or how we would know to use certain functions with certain word problems or real world applications. So in this first example, we have linear. And in linear, obviously we've got a straight line, and we have linear functions. You're not going to write all this down. I'm going to have you write some other very specific things down. Okay, so linear says that we've got a continuous rate of, a constant rate of change. So that is one thing that we should be looking for. They could be added or subtracted. And that actually stands out pretty well. If you remember, we have some common rate words that we end up seeing. So if you will list out these words per, for each, every, there's a few more, but those are our common words for linear type functions. For exponential functions, we should note that we're looking for something that has a common ratio. Now, we might see the words growth or decay for exponential functions. Something else that we also see very often for exponential functions, we have questions about doubling or tripling, or we might even have questions about something happening half. But the biggest giveaway for exponential is we have percentages. Anything that's going to be a percent is going to be an exponential function, like 99% of the time. Okay, and then our last type of function that we need to talk about is quadratic functions. And again, we have just been talking about these in class. So we have quadratic functions that are used to model situations where we're talking about reaching a maximum or a minimum. The things that really stand out here, the types of problems that we have seen, is when we have projectile motion problems like we did yesterday, with our initial velocity and our initial height. We also have area problems that we did the other day where we're talking about maximizing area. A lot of times profit problems end up here too, especially like we said when we're talking about maximizing profit or space or something to that effect. So make sure you have these three kind of laid out for yourself as well in the back of your notes for word problems, and we will use these in class tomorrow.